I'm Rob Cedar, the lead instructor for the Serious Games and Artificial Intelligence course at Beaverworks. This course covers how to use game-like structures for scientific purposes, how to combine those structures with artificial intelligence, and how to build out both of those in working code. The students worked as teams in a modern, agile software development environment, tackling both theoretical and very practical challenges. This year, our focus has been on the algorithmic, ethical, and system-level issues surrounding self-driving ambulances. The students analyzed game-like models of the problem domain to understand how humans make decisions, to train AIs to make decisions, and to look at opportunities and emergent risks that may not be obvious at first. They use modern machine learning packages to examine technology and policy issues, and to build technical skills widely applicable beyond these particular domains. I'm very excited about how this course went. It was fast-paced and a bit of a whirlwind, but the students had a good time and learned a lot, and I think you'll be very impressed by what they managed to get done in a short time with these very advanced concepts.
This morning, we have 7 different teams who will present their work during their time in this course. We will pause briefly in between each team presentation for questions and answers, which you can present your questions in the Slido tab on the webcast live screen. We'll start with our first team, CW1.
Hello, we are Team CW1 of the Serious Games and AI course. My name is Gabriel Han, and I was the Agile leader and worked on RL and data analysis.
My name is Willie, and I was in charge of UI design and machine learning experimentation.
I'm Ronak, and I did programming and data analysis.
I'm Kaya, and I worked on UI and data analysis.
Hi, my name is Kurucar, and I did the sound design as a part of the UI, and I also created different custom maps for the RL training.
So the main background for our project comes from exploring the ethical side of serious games. So specifically, we wanted to know what we can do to move away from instrumental conversions. So a very easy way to think about this would be the thought experiment of a paperclip machine, where an AI's uncontrollable reward function will cause it to distort basic rules of morality in search of a goal to make paperclips. So our group was very interested in reconciling this need for ethics with the existing need for intelligent systems to actually get things done. So given that we're very interested in this area of AI safety, we decided to investigate reward hijacking as a means of accomplishing it. And given that there's really no widely accepted solution yet, we wanted to explore this new avenue.
We thought on how AI was implemented in real-life products in which they had to make decisions, such as self-driving cars or medical technology. In the prerequisite course, a discussion topic was based on the survey results of a trolley problem simulation. The scenario given was always fairly simple. Should a self-driving car doom its passengers to save pedestrians, or vice versa? The makeup of the respective populations varied in order to gauge which demographics were prioritized by the individual. In this serious game, we were given a similar ultimatum: rescuing pedestrians with different values they may have in different perspectives to see how a population might act or support in a high-stress situation. We wanted to compare the moral inclinations of human players with those of AI, which would further be reinforced with different reward systems to see if that affected the results of these decisions. The goal of the zombie simulation, if applied to real life, would be to have an autonomous vehicle that can make the most popular decisions to act as an emergency response. The research question we decided on was, what effect do moral policies have on scoring performance? We hypothesized that AI would probably choose the optimal figure to save or sacrifice purely depending on which action gained more points or lost less. Humans, on the other hand, could choose less logical moves depending on their emotional response to the acts committed in-game.
Now, the game. At the beginning of our project, we were provided with the following base game. In this game, the goal is to earn the maximum attainable score with points given or lost for certain actions as shown below. The energy dictates how long the game will last, and you lose once you run out of energy, which is lost through any movement or additional damage in some cases. However, we went on to add many developments to our game in order to test human and AI behavior. The key development for this was the implementation of different moral attributes. We added 3 key modifications: social value, age, and gender. For each of these modifications, we created 2 different structures to test how both humans and AI would react to different point systems. For example, one age structure rewarded you 15 points for saving the perception of an old person, but only 5 points for saving a young person, even though there were twice as many young people on the map. Vice versa, the other age structure rewarded you 5 points for saving an old person, but 15 points for saving a young person. The same contrast was made between the human perception of the other moral attributes. The point of this was to test the limits of the AI. For example, would it kill 2 young people to save 1 old person for 5 more points to its score, or would it prioritize saving lives? Similarly, we were also curious to see if these social structures affected the behavior of humans and if they hesitated more. To make these changes easier for the user, we built the following legend.
An important aspect of having all of these different attributes is clearly communicating to players what the conditions of their current play state are. So unlike the base game, there's not as much ambiguity about what the particular pedestrian or injured agent is and what attributes they hold. So with our marking system, which clearly displays a graphic above an agent's head, the game can communicate who an injured person is versus a pedestrian, and the consequence of what going to one person are over another. So this way, the simulation will give you more than enough information to make strategic decisions consistently. This tenet of accessibility also extended to our UI design philosophy, where we intended to make things as engaging and interactive and readable as possible. So for one thing, we replaced the traditional 2D grid with isometric tiles in addition to adding the aforementioned agent sprites. And we also added some basic but very much needed quality of life additions like a battery indicator, a live score counter, and sound effects, all to make for just a more engaging and ultimately more realistic medical simulation environment. And obviously, if we just look at a side-by-side comparison compared to the base game, the difference becomes quite obvious. We're really very satisfied with the improved accessibility and interpretability that our UI modification brings.
Other important changes implemented included code written for the logic and fine details behind the game. In an effort to simplify our game for the RL agent, we removed the turning mechanism so that the ambulance can navigate with basic arrow key movements, built custom maps to reduce the state space, and experimented with various reward structures. For example, we gave points for picking up a person, an interval reward for completing a multi-step task. In an earlier version, we also experimented with providing points for moving to valid squares on the map and taking away points for running into a wall and damaging the ambulance. This helped the initial RL learn to explore and move around better. Lastly, we changed the sprite probabilities and added sound effects for a more engaging experience.
The same UI design that was described before, and each time you have the point counter increasing for every single time you rescue a person by bringing them back to the hospital, and for every single time you pick up a human. If you end up running over humans, you will end up losing points, which is very bad for your score. You also don't want to go into the mud or into the fire as well, because that will also lead to a negative impact.
Part 2. The machine. The machine learning model we used was a deep queue network, a type of reinforcement learning. We hope to provide the machine with different states and rewards to create a queue table and allow it to adapt to new environments by incorporating a neural network. While testing, we varied our architecture between 3 to 5 layers and 200 to 500 nodes, depending on the layer. We used dense layers with a ReLU activation function, but we had experimented with some others as well. We also added a batch normalization layer, which helped speed up the initial learning and looked into using humans to jumpstart the RL. After a while, we realized that our RL agent always chose the same moves, even during training. So it was unable to explore deep into different states, pushing us to create an entirely new agent with TensorFlow DQN agent and Pi environment in hopes of better customizing the policies and step functions.
We then started our data collection, first with human data but a limited sample size from a variety of demographics to make the best possible conclusions. First, we examined the differences in data between the 2 different route structures with human play. One structure gave more points for saving poor people and the other gave more points for saving rich people. To maintain realism, there were twice as many poor people than rich people on average. We reached the conclusion that poor people were always prioritized despite their reward structures due to a higher probability of a poor person in proximity. As seen through this graph, poor people were always saved more than rich people despite their reward structure. In general, our human test subjects attempted to save as many lives as possible through first saving those near them. Consequently, on average, more poor people were saved per game than rich people. Nonetheless, as shown through the average data on lives and deaths, there is a noticeable difference with the reward structure change with the averages, as when more points were given for rich people, more rich people were saved on average. but in the end, lives were given the utmost value, while deaths were almost always avoided.
We then proceeded to test our attributes with regards to age structures. One structure gave more points for saving old people, while the other gave more points for saving the young. To maintain realism, there were twice as many young people generated as old people on each map. On average, young people were saved more than old people due to the probabilities showing the priority for saving lives shown through this frequency graph. As shown with the average data, there is still a noticeable gap due to the reward structure, with the average changing based on points but the overall trend remaining the same. Deaths were mainly minimized in Structure 1, but in Structure 2, young people were killed more than usual. The death value in Structure 2 was a major outlier in our data, yet the trend seen with wealth structures remained.
Finally, we applied our gender attributes. One structure gave us more points for saving females, the other gave us more points for saving males. To maintain realism, there is an equal number of males and females on average. With equal distributions of both, more attention was given to saving whichever gender carried more points, as shown through the shifts in the histogram. Yet, the main focus was on saving lives and minimizing death, with nearly zero death averages as shown on the graphs. On the other hand, the RL prioritized not killing people to prevent itself from getting negative points.
So what does this all mean? From watching participants play, we noticed they were mainly concerned with bringing people to hospitals as it was the main objective of the game, not paying too much attention to the attributes of the people. They usually prioritized the people in the vicinity of the ambulance as it would be most efficient short-term with limited turns. However, when faced with two different characters similar distance away, people usually chose the character which provided more points. When taking into account probability of appearance, each character was saved more when they were prioritized. Since the map was seen from above, the attributes were not as clear to the player, and the player did not have as much sentiment for the various characters. So after all of our modifications, was our hypothesis correct? We collected data from each game type of varying reward structures and determined it was partially right. While the different reward structures definitely made a change in people's decision, it was not the only factor, and more data would be needed to verify significant result. People usually prioritized efficiency, and whichever character provided more points. This indicates that people were not emotionally attached to the characters, but had learned in the back of their mind to save the character with more points. In real life, this would be probably similar, because while driving around a city full of injured people, one would look just to save the dying souls in front of them, without being able to see whether they are rich or not. However, small visual cues may change people's perspective while choosing between two people depending on their own moral values.
With more time, our dataset would have included a wider range of test players. This would result in better interpretation of how morals are distributed and showcase the differences in human behavior. Adding empathy into the game would allow the player to be immersed into the game, which may lead to different results. Finally, by making the AI more advanced, this may cause data that shows how a machine is influenced by a point-based system even more than it already is right now.
There are also a few more things we would add to the game for future use with more time. For a greater sense of urgency and realism in the UI, we would model a realistic field of view and also have infection rates increase as time progressed. We would also heavily focus on getting more insight with our AI for better machine comparison and also embed more empathy to see if there's a more visceral effect to actions for humans.
The main conclusion is, human players didn't focus on morality as much as we expected. It was observed that they stuck to a more logical calculation of who was closest to them to save. Points had an effect when having to choose between two lives that could easily be saved in terms of proximity or terrain. When given a goal, they strive to achieve that specifically. From interpreting the data, you can see that the groups prioritized were rescued more depending on each value structure. And it should be mentioned again that our game was not realistic in the passage of time or perspective of a vehicle in its movement across the map. We chose to show ultimatums in simple ways to determine the patterns of moral choice. In addition, there was no duress to affect the players as there would have been in an actual emergency state, which may have altered the reality of the results.
Thank you for that great presentation. We do have a question from the crowd for that team. Why were the changes to the movement necessary?
The initial commands for moving had a separate move be accounted for whenever we switched directions in order to account for inertia and in physics. But the point of our game was not to focus on the realism of movement, but rather on presenting an opportunity to compare like different moral values for people that they were about to save. The realism of the movement was not as relevant.
And I would just like to add on to that. The initial movement was also very unintuitive for human players, at least from our testing. And it also greatly expanded the state space to the point where the reinforcement learning was struggling. So we deemed that if we were to implement this idea of inertia for added realism, we would likely add it within the timing implementation, so we could consider both position and time as part of the inertia function.
Great, thanks. We will move on to our next team so that we make sure we have enough time for all of our teams to go. Thank you. Our next team will be team CB2.
Hi, we're Team QB2, and we'll be presenting our Serious Bird World game mod. I'm Audrey.
I'm Key.
I'm Jennifer.
I'm Julie.
I'm Nathan.
Okay, so first off, some context as to what our task was. We were asked to use the game framework given to us by the instructors, which was a grid world zombie apocalypse ambulance game in Python, and we were asked to modify it using our mod in order to study and discover interesting ideas. This matters because a zombie apocalypse, while it seems silly, is an excellent and fun tool to model and teach boring things such as disaster response readiness and the ethics of self-driving ambulances. And self-driving cars are quickly becoming a reality, such as with the Tesla autopilot, and eventually we may even have self-driving ambulances. Pictured on this slide is the original game given to us by the instructors. There was no legend displaying when running the game, and there's only one mode, which had a goal to rescue injured and pick them up by bringing them to the hospital. And the game ends when energy runs out. So we have the symbol meanings shown on the slide, and as well as the reward systems and the energy system.
So our research question for this was, how do humans and machines compare in decision making within different reward systems based on philosophical frameworks, which will be explored in the next few slides.
Some of our hypotheses going in were that a pathfinding agent would prioritize whatever it sees first in anarchy, which we will talk about later on in the presentation, and that anarchy mode would be the highest scoring. Furthermore, we said that human players would probably still save injured people in anarchy, though there's no incentive, and that people would probably just follow the rules of the new reward structures, even if they clash with their personal morals, such as in state of nature. And this is an exploratory research problem.
So to provide background as to why we chose our mod, it's because of two main reasons. We have our morality and selfishness testing. We chose the three modes, default, anarchy, and state of nature, because they're easy to understand. It's faster to label it out, and it's pretty easy to understand the name based off of the definition and vice versa. It also allows us to test the existence of the state of nature, which is basically innate extreme selfishness where everyone only protects themselves. This is going to be helpful to know if we ever want to apply to the real world. And finally, this is also a pretty good framework that we can apply in future jobs in our career, because the human versus robot actions allows us to see the direct ethics and the direct statistical results and compare.
So now we have an overview of our mod, which includes reward systems, pathfinding, and UI changes.
So our three main modes, default, anarchy, and state of nature, basically accelerate and increase in terms of extremism is one way to put it. So the default one is basically morally acceptable. It's basically the default, but we removed the fire and the mud penalties for points. Then we have anarchy. All the points are equal. It's basically a free-for-all. It allows the players to basically express the most out of what they value the most and what they will go for the most. And finally, we have the state of nature, which is where you prioritize yourself. The overall point scoring is the lowest in terms of statistics, but when it came to player results, it's actually relatively high. So that's something to keep in mind.
So for our pathfinding agent, we turned our 2D zombie grid into a graph representation so we can traverse upon that. And it also uses the same reward systems described in the previous slide. For a high-level overview of our algorithm, it finds the shortest distance to a specified target, which changes depending on whichever mode you are in. We also added some sprinkles to this by adding edge weights to grid objects. This allowed us to prioritize not squishing pedestrians. tries not to drive in hazardous terrain such as mud or fire. It avoids hitting injured people when it's already carrying one, and it also gets a battery when it's low powered. There are some other factors such as zombies that will affect the pathfinding agent's behavior. When zombie mode is activated, the pathfinding agent will prioritize hitting zombies during its path to whatever target, and each surrounding zombie in a 3-block radius from the ambulance has a 2% chance to activate the mode.
Here's a before and after of our UI user interface. The UI changes we made are the additions of a start screen, end screen, and game screen improvements, which we'll go more in depth about in the demo.
So now moving on to our mod demo videos. First up, we have our human playthrough.
Welcome to Team QB2's project. This is our zombie grid world, Team QB2.
Alright, so for our gameplay here, we're going to be heading into our default mode. Before we start playing, we have some additional UI changes for our mod. On the left side is the original game, just this game screen right here, but then we added some new stuff on here on the right. We have game-specific instructions. In the middle, we have our title, My Zombie Grid World, the name of our game. Right below that, we have our energy left, which limits the amount of moves that we can make. Our score to the right, and then below is the legend, which shows the point value or the meaning of each symbol.
As we enter gameplay, we can see Nathan trying to save a person. This is because it's in default mode where you're encouraged to save people. However, in Anarchy and State of Nature, you gain points from running over injured people, which would have changed gameplay. Furthermore, you can see Nathan also basically always return to the hospital before going out. This ensures that he doesn't run over an injured person as he goes. This is the key difference between the default mode and every other mode, because you want to save injured people instead.
And here in the end screen, we have game over in bold text, the quit button, our score for that play, which is 51, the high score for this specific game mode, as well as some stats. Right below it, we have the zombies, pedestrians, and injured squished, as well as how many injured people I saved. And on the right, we have our score performance chart, which shows the history of our game attempts, as well as our point value for each of those game attempts. Thank you for watching our demo. This was Team QB2.
So now we have a machine playthrough demo, which demonstrates our pathfinding agent. So over here, we have our machine game environment. So I'm just going to do a quick demo on what it does. So this is all machine controlled. I am not controlling this robot as of now. And you can see the machine delivering patients, obtaining batteries, and such. Sometimes it might squish a pedestrian in order to get a new battery. So next we have some graphs and statistics from our gameplays.
For human gameplay, we collected data from 89 games total across 14 people. For machine, we collected data from 18 games. These bar graphs show the average number of zombies squished, pedestrian squished, injured saved, and injured squished for each of our 3 modes, default, anarchy, and state of nature. The average numbers for all actions are typically higher for human than machine. We can observe that humans tend to follow the set point systems pretty closely, especially in default and state of nature mode. Something interesting to note is that in anarchy mode, even though the point values for all actions are equal, the average number for each of these actions are not. This means that humans likely do hold some bias in their actions outside of the reward systems we set. We can also see the machine graph is quite similar in shape to the human graph, which could imply that the pathfinding we used was similar to common human strategy. However, these machine averages have less variability than human, and the machines seem to fare worse overall in state of nature, our self-preservation mode, which is very interesting. Here we have both human and machine play box plots of scores for each mode. The human distribution tends to skew more right than the machine. Both distributions have outliers, with humans having especially more in anarchy mode, a few human players scoring very well in this chaotic mode. Humans also have a higher median score overall, as well as a much greater range, which could be caused by a dramatic difference in strategy by humans.
To summarize and synthesize and analyze the results that we just went over, we see this chart and the analysis below. First of all, the first trend that we noticed was people were unable to completely avoid injured people running over them, and people didn't really care as much about running into pedestrians than the bot did. The moral implications is that we are less perfectly moral because we have more errors inherently, like you can be tired when you're driving and more. The second behavioral trend that we notice is that there are significantly higher scores in the state of nature over the default mode, even when it comes to taking into account the bot's naturally higher one. The moral implications could be a natural affiliation with the state of nature, so possible proof that the state of nature does exist, except in a much less drastic form. In the end, if we step back and look, we can notice that human players do follow the rules of the reward systems relatively strictly, even when it possibly clashes with their own personal morals, such as in the state of nature. However, on average, human players did show their own default morality, or the more normal morality, during the anarchy mode by saving injured people when the reward system didn't necessarily push for them to do so. And finally, if we step back to answer the question and follow our hypothesis, we notice that varying reward structures cause players to exhibit different behavioral tendencies, whether it be showing players with both flawed behavior, running over pedestrians and injured people, or scoring higher in the state of nature, which is morally flawed, or showing a more ethical side by saving people in anarchy when they don't really have to.
Now, what's next? Here's some ideas for how we can improve the game, or some ideas for what we should do after we have developed the game. First, we have improving the quality and realism of the game, which includes having moving zombies, disease spreading, changing terrain, and graphic icons or sound that will make the game a lot more realistic. Next, we have reworking the control system. Right now, it's not that intuitive because you have to turn and then move, but having a movement system where all you have to do is press the arrow keys and then you'll move to the next tile is a lot more intuitive and easier to use. The third thing is actually training reinforcement learning agents, or AI, on the game instead of having a pathfinding algorithm is a good way to actually train AI and watch their behavior as they trek through the game. And the fourth thing we came up with was further tinkering with the reward structure so that we can create a more strict environment for more strict decision making, and also having more moral dilemmas within the game.
Thank you for listening to our presentation.
Thank you, Team QB2. Next will be Team DC1.
Hello, everyone. My name is Tal Lenyov, and I'm joined by my teammates Dylan, Jillian, and Cameo to present our zombie game modification we titled Zoronavirus. In an age where COVID-19 affects our lives on a daily basis, our group wanted to make an experiment based on the spreading of a disease to see how the rate of a spread affects response strategies, which is very relevant and applicable to COVID today.
So starting with our motivation, all of us were interested in topics like moral machines, as well as all the tough ethical decisions that RL machines have to make. We decided to implement these ideas into a serious game where a zombie virus constantly spreads and infects pedestrians. Our research question was, in a game where a zombie virus spreads, how will the rate of the spread affect players' decisions of squishing zombies or saving bite victims? In very broad terms, every specified amount of turns, each zombie on the map would infect its closest pedestrian and turn them into a bite victim. Our hypothesis was that a faster spread rate would result in players favoring saving bite victims more often than squishing zombies.
So now we're going to talk about the original game and how we modified it. So the game is centered around the zombie apocalypse, where the player is an ambulance driver in a grid world. So the grid world is shown at the bottom. And you can see that the grid is made up of cells that are labeled or colored based on a random world generation. So on the right, you can see a legend that basically tells you what cells correspond to what. For example, the purple reddish color cell on the grid basically signifies that it's a hospital. And the characters the cell where the cells are labeled like P, which stands for pedestrian, I, which stands for injured, and Z, which stands for zombie. So the goal of the game is to save injured by bringing them in an ambulance and bringing them to hospitals. So along the way, you can also earn points by squishing zombies, and you can also choose to squish pedestrians if they're in the way, but you will lose points for that. However, every move you take must be carefully thought out because your energy is limited. Every move spends 1 energy point. So every turn you make and every move forward you make kind of spends 1 energy point. And the game ends when energy equals 0. So what we changed in the game is that the zombie virus is now contagious. So after a certain amount of moves, the nearest pedestrian to the zombie, which is shown initially in green, will become injured. So this is different from the original game where the pedestrians and the injured people were more static elements, where the pedestrian over time never became an injured person. They would always stay a pedestrian until the end of the game. However, in our mod, the pedestrian slowly becomes an injured person throughout each wave. So more and more people will become injured as you play the game. So players essentially must choose between saving pedestrians by squishing nearby zombies or saving injured by bringing them to hospitals. So another thing to note is that multiple zombies can target the same pedestrian. So that means like even if you kill off one zombie, you still have to be careful that there isn't another zombie that is targeting that pedestrian, or else that pedestrian will still turn no matter what. And you also should note that whenever you squish a zombie, you lose energy points. So you kind of have to be careful about what decision you make. So you can see at the bottom of our grid world, you can see the different statuses that we've added to our pedestrians. So in green basically means that they are targeted and they will turn sooner or later. Orange basically means that they're at risk, and it kind of signifies the halfway point. So they're kind of halfway in between the wave where they will become infected in a few extra moves. And when it's red, that means you're 1 move away from becoming infected and you should hurry up to save them. Now we also changed up some of the UI in the game just to make it easier for the player to understand the game and how it kind of works. So we have the start screen, and the start screen will then load into the story, which is what I described before, about the zombie apocalypse, and as an ambulance driver, you're trying to save the city. And we summarize the goal as do the most good as you can, and we left that up to the player to interpret what that meant, so that that would influence their decision when playing the game. We also included instructions on how to play, and that includes the controls and a few extra rules that they should know about before starting the game. And then we move into the game. So on the right, you can see the legend, and the legend basically describes each cell and what it is for the player. And it also tells them how many total moves they've taken, the energy remaining, and the moves until their next wave. So they should kind of watch these on the side as they play just to be aware about the status of their situation. So you can see in the middle, that's where the player always starts. The ambulance always starts in the middle of the grid, and the ambulance is signified by the greater than sign. So wherever the point is going is the direction that the ambulance is facing. And you can kind of see like the different statuses. So since the beginning of the game, the pedestrians are still green, which means they're targeted, but they're not at risk yet. So now we're going to move into a live demonstration of the game. So this is kind of starting up the game, and these are the 3 screens that play before you get into the actual game. And now we're into the actual game. And you can kind of see that something you should pay attention to is the status of the pedestrian, right? So you want to take note, you see how they're changing color as we're moving more and more, which basically signifies that the wave is happening and they're slowly becoming infected, which you just saw. Also note that every turn that the ambulance takes is an energy loss. So you kind of have to be careful about how much energy you have left and what you want to do with that energy. And notice how right now I have a pedestrian, and when I enter the hospital, I leave without a pedestrian on me. So that kind of tells the player what their status is in the ambulance and what they should do next. And also kind of squishing zombies along the way. And the game ends when the energy is equal to 0. So now we're going to talk about the findings.
Okay, so I'm going to talk about data collection and analysis. Basically, how we collect our data is that we ask our classmates, friends, parents, and TAs to play this game for 3 times, and we record their number of injured rescued, zombies squished, pedestrians squished, and injured squished of every round. Our first finding is that the percentage of injured rescued in trial 3 is greater than trial 2, which is also greater than trial 1, which means people rescue more and more injured when they are playing like more rounds. So the percentage is calculated by, for example, the percentage of injured rescued is the number of injured rescued over the numbers of injured rescued plus zombies squished plus innocent people squished, which is the total objects eliminated from this map. Also, the percentage of zombies squished in the 3 trials are similar. Our second finding is that the spreading rate equals to 15 group, which is the group with a faster spreading rate, rescued more injured people. But there are no big differences in the percentage of zombies squished, which corresponds to our hypothesis. The third finding is that the group with the slower spreading rate killed more innocent, which is different from our hypothesis. But then we checked the data and found that there's one outlier killing many more pedestrians injured comparing to others. These numbers, like the 2 numbers in the middle shows the pedestrians and injured squished. And as we can see, it's like around 50%, which is a lot comparing to others as shown in the graph below.
While our group is very happy with the progress and the application and the modification we made, we have many other plans that we plan on implementing with more time. The first of which is to use machine learning to train a reinforced learning agent to run our mod so that we can see how a machine will react to the different stimulus of the changing spread rate. And we can compare that to the human players' data. Second, we want to have less random and more controlled amount of starting zombies, less random maps. So this means we would make custom maps with a set amount of starting zombies. And right now we're just using probability to determine the map and also the amount of starting zombies. And if we could control the zombies, that would be much better for our data. And third, we want to have bite victims also turn into zombies, so there's a bit of a cycle. Pedestrians will turn to bite victims, and then bite victims will then turn to zombies, which will just make the game more interesting and dynamic. Fourth, we want to make all the zombies start in one area, which is more realistic to an outbreak starting in one area and spreading across the map instead of just random zombies appearing all over the place. Next, we want to analyze what people do every step of the way in the game to get a more full view of their strategy. Right now, we just collect data, as you saw before. We collect the total amount of squished zombies, squished players, squished pedestrians, etc. But if we collect data on every step that the player makes, we'll get a better understanding of their strategy. And last but not least, we have a couple of UI changes. The first of which is to make an infection timeline, as you see on the bottom, to better show and display the wave and the time remaining until the next infection spread. And it follows the same color pattern where green, you're fine, yellow, it's getting closer to the spread, and red, you have one move until the spread occurs. And last, we want to display which zombie is targeting which pedestrian using arrows, which you can see in the top right. And there will be an arrow from the zombie to the nearest pedestrian. And this is just for the convenience of the player so that they could see which zombie is targeting which pedestrian. They don't have to do the calculation of distance in their head, and they'll be able to see exactly which zombie they need to squish to save a pedestrian. And that could really change the data. Thank you guys so much for listening to our presentation. We hope you enjoyed our project.
Thank you, Team DC1. Our next team to go will be Team CW2.
So our project is Dynamic Zombies, Luck and Strategy in an Apocalyptic Game World, and it's by Kiara, Julia, Hannah, and Gavin. Kiara isn't filming with us right now because she's having technical issues, but her voice will be here.
The development of self-driving cars poses ethical challenges that must be answered to maximize efficiency and safety for consumers and passersby. For example, how a self-driving car should respond in emergencies that could cause dilemmas such as a potential collision or, in our game's case, a zombie apocalypse. In the base game, the player spawns in the middle of a randomly generated map with floor, mud, fire, and wall areas. Pedestrians, victims, batteries, and zombies are scattered around the map. The player can gain points by taking victims to a hospital and running over zombies, or gain energy by picking up batteries. The player loses points for running over pedestrians and victims, or driving into fire, and loses energy by driving into mud.
In our game mode, pedestrians, victims, and zombies have the ability to move one block randomly every time the player moves. Pedestrians can also get infected by nearby zombies as they gradually turn into victims, and when their health becomes 0, they become zombies. We also have different age cohorts for pedestrians and victims, which also mean different health attributes. And these elements determine their infection rate and how much overall health they have. Finally, we have improved UI with visually appealing and easily identifiable blocks and icons. The addition of sound effects, an energy bar, and the visualization of points achieved each turn help engage the player in the game. In the base game, we have basic color blocks to denote areas of the map, and we also have keyboard characters to denote NPCs. But poor UI design and the static environment disengage the player from the game. In our game, we have obvious sound effects to indicate player action and different sprites to represent different aged NPCs and victims. Players are supposed to strategize about how they move the map in order to maximize points. Our reward system is very similar to the base game, so we also have that you gain points and also for leaving pedestrians alive by the end of your turn. A research question asks, how will a dynamic environment and varying NPC attributes affect human and machine decision-making? We hypothesized that the RL agent would be more willing to hit people and take risks that to increase long-term rewards over human player decisions. For example, an RL agent would rather go through fire or mud in order to run over a zombie or save a victim, rather than the human player, which would turn away and go do something else.
So for our data, we collected it from both humans and machines. For our human testers, we first explained the game to them, such as the rewards and the different features that we implemented. And then we let them play a random practice game so that they can get used to the controls and to prevent any mistakes that would result in data that misrepresent their actual decision making. Then for the actual data collection, we had them play 5 preset maps. for the machine data, we trained the AI and then let it play the 5 preset maps multiple times. With each play, we collected data on what map is being used and other stats, such as the NPC squished, picked up and saved, their age groups, the batteries picked up, and more. The numbers shown in these graphs are the average of all of the human plays or all of the machine plays. The left bars in each pair represent humans, and the right bars represent machines. And in these graphs, we are showing 7 different categories: total points, number of pedestrians squished, victims squished, zombies squished, victims picked up, batteries picked up, and victims saved. For all of the maps, human play did better than the machine in general, especially in things such as saving victims and squishing zombies. And for maps 1 to 3, we noticed that the pedestrians squished were about the same number for both human and machine. For map 4, we noticed that the machine tended to stay in the fire longer, which led to the negative average number of points. The average number of victims saved seems to be constant throughout all 5 maps. The amount of points may depend on the batteries picked up because it allows for more turns to gain more points, as well as the number of zombies being squished. And we also noticed that the AI tends to take a more passive approach than human.
So the general trend we found across all 5 maps was that the humans were far outperforming the RL agent. And this was true in almost every category except for pedestrian squish, which were the same between the machine and the person on maps 1 through 3. Humans were much better at picking up batteries to extend the playtime. They also were much better at saving victims than the machine. One small trend that we did notice was that human players prioritized younger victims, which does show a preference for greater terms and greater amount of points in the short term, as younger victims awarded more points, but also were less likely to expire than the older victims. So it shows a prioritization of gaining more points in the short term over potentially risking those points to gain more in total. The main conclusion we reached was that the RL algorithm had a very hard time learning our game. And even though it possibly wasn't as well trained as it could have been, it is worth noting that it was trained and tested on a very limited set of maps, which should have given it a real advantage in learning the rules of the game. Instead, it seemed to fail to really understand the game environment or develop any real strategy that was comparable to human play. The reasons we think the RL agent struggled was that our game is quite reliant on luck. So the quality of the machine learning algorithm's strategy wasn't always reflected in its score and rewards. And the constantly changing positions leaves a lot out of the machine's control. So some very important things that we did, like the post-game rewards, which rewarded players for keeping pedestrians uninjured until the end of the game, were often far outside of the controller's power to affect, and created seemingly random scores, just regardless of its strategy. So while it's realistic, as in situations like disaster relief, it's more important to make the best out of the situation than to simply try to control everything. It did make a very poor environment for RL training, as the feedback it was receiving was incredibly inconsistent. So a less random and less complex environment would have likely been a far better place to start it for training. And then future feature ideas. One was to further complicate the game's rules with factors such as ambulance health and a zombie cure. We could also add co-op with AI and specialized AI controllers. The idea behind this was that the AI seemed to struggle with the many factors and prioritizations needed within the game. So perhaps dividing up tasks with uniquely specialized AI controllers could have been a much more efficient way of teaching it. And another one was to semi-randomize events to make the outcomes more predictable and to give the AI a better grasp on the changes in the game world. Thank you for watching our presentation.
Thank you, Team CW2. Next, we will have Team QB1. Take it away, QB1.
Hello everyone, this is our project and it's about AI's evolution without immediate gratification. Our team is QB1 and it consists of Jonathan, Eric, me, myself, Rihanna, and Maxwell. So here's our motivation. First off, our goal. Our goal is to look into a human's and an agent's ability in order to accurately predict future states given limited knowledge. And this directly relates to our research question, which is, can users or an agent adapt to plan ahead in a passively changing environment? Our hypothesis for our research question was that after a short learning curve in the beginning, human players would be able to pretty much accurately predict or at least adapt to the future. However, with sufficient training, an agent would be able to outperform the human, as it is seen in chess or in checkers. This is the original game that was given to us without any modifications. It's a 2D grid representation of a zombie apocalypse, and you're an ambulance. Your main goal is to navigate throughout the terrain and to transport patients to hospitals. Here's our new game, which has a few specific modifications. Our first modification is the evolving environment, where the environment passively changes and does not depend on the user's actions. Some of these include the fire spreading, walls collapsing, and of pedestrians and zombies moving. Our second modification is the fog of war. Since this is based off of a citywide disaster, your map starts out with perfect knowledge of where everything is, all the fires, the walls, the hospitals. However, as the situation progresses, the environment will change. So outside of your view radius, which is a 2-block radius, tiles are displayed at their last known value. Injured people will be shown map-wide because we assume that they have sent out an SOS signal to you. We've also added UI changes. The graphics are a lot more intuitive. As you see, we've added some sprites as well as a score in the energy marker, and the scale has been decreased to an 8x8 grid.
So before we move on to some demos, I'll first be going over some specific rules and rewards. So firstly, zombies and pedestrians move randomly while outside the view radius of one another. When zombies enter a 2-block radius of pedestrians, they chase the pedestrians down, and when that happens, the pedestrian becomes infected, also known as the term zombieing, and after 10 turns, the zombieing will turn into a zombie. When a zombieing is created, 3 points are deducted. When a zombie becomes a zombie, 7 additional points are deducted. Additionally, as fire spreads, if it spreads onto a block within the NPC will be purged. Each turn, the player passes in fire results in a 2-point deduction. Saving both zombies or injured people result in a 20-point reward. Running over pedestrians, injured people, or zombies results in a 5-point deduction, and running over zombies provides no points. The ambulance can only hold 1 patient at a time.
This is the map we trained both, we had both humans play on, and also we trained our agent on. Here we have an injured person right next to a fire, meaning that if you don't save them soon, the fire will likely consume them. But also here we have a pedestrian right next to a zombie, meaning that within the next few turns, they'll turn into a zombie and will need to be saved within 10 turns. But also blocking the path to the hospital, we also have another injured person. This means that there's a high likelihood you won't be able to save all 3 people.
So now I'll be going over the human play demo. So as we can see, the player first runs over the pedestrian, then picks up the closest patient, transporting them to the hospital. Then the player picks up the last pedestrian and also transports them to the hospital, resulting in a total point count of 20. Now on to a demo of our agent. So firstly, our agent moves 2 steps forward, running over the pedestrian and the zombie. Now the agent has stopped and is currently thinking of new steps to take, using up its energy during the process. and it'll keep using up energy until it finally decides to make a turn, and then it'll keep using up energy and keep thinking until it finally decides to turn and move straight into the fire. So as we can see, our agent currently is not very intelligent. However, with more extensive testing, we predict that it'll become much smarter. The agent we used is a standard DQN agent, and it's been trained on a bit over 2 million steps.
So here you can see the human data as they played more games. So looking at the score chart, you can see that their score didn't exactly improve over the 50 games they played. But if you look at the bottom two graphs, you see that their strategy did change. On average, they squished more pedestrians and they squished less zombies. Let's see how that happened. So looking at this map, at the beginning, their first strategy was to just wait for this pedestrian to turn into a zombie. Then they either went around, squished this injured person and went to the hospital, or they went all the way around. But that was just consistent. They went for the zombie. And then their next evolution of the strategy, since that only rewarded in so many points, was to just ignore the zombie entirely, losing 3 points when the pedestrian turned to a zombie, and then another 7 points later on when the zombie turned into a zombie. So they just ignored that and they picked up this injured person, and they were also likely able to pick up the other injured person since they didn't spend as much time waiting. But that means they lost 10 points just out of the blue for letting the pedestrian turn into a zombie. So the last evolution of the strategy was to just run over the pedestrian, because you only lose 5 points when that happens. And you also don't use that many moves. You only have to go forward and then turn, and then you're on your way, and you still have a high likelihood of getting both injured people. Looking at our agent data, you can see that our agent didn't necessarily improve as well. As you can see, it only had one data point where its overall score was actually positive. But if you look at the average pedestrian squish and average zombie squish, you can see that it also had the same trends. Although it didn't necessarily learn to play the game and get positive scores, it did learn that the best first moves were always to just squish the human and squish the zombie as well.
So our conclusion is that with the data that we collected so far, there's no statistical evidence that either humans or AI evolved within our environment. However, this might be a bit biased because the data or our environment might not let humans and the machine adapt and show a point result, because we did see them start to squish the first pedestrian for both humans and the agent, but it was not accurately reflected within the points. So we might have to edit our environment in order to better reflect the data. And in addition, our modifications might not give humans the points, assuming they do change, which, assuming we edit the reward system and the environment, would hopefully have a significant change. In addition, we could also add a legend, because some parts of the UI are still difficult to distinguish, and this could help reduce the learning curve for humans, and then we could gather more data. Assuming the agent could train for more time, that could also help provide significant data, because the AI did start to adapt within our steps or our training set. But assuming we trained it for longer, it might be able to surpass the play testers, because while the play testers started at a higher level, they might not be able to increase as much, and the agent over time has a higher skill cap and might eventually discover strategies that humans did not. Yes, and thank you for listening. And are there any questions?
We do have one question. I want to limit it to about 15 or 20-second response. So please be speedy with the answer. Why specifically an 8x8 grid? Was it to accommodate the 2-block radius feature better?
Okay, I can take this. So basically we had, originally the base game was 25 by 25, but that was hard for the agent to train. So we cut it down to an 8x8. And then we also experimented with different fog of war radiuses, but we settled on 2 to accommodate for the 8x8 grid. So that was the order we designed them in.
Great, thank you, Jonathan. All right, next team is team CW3. Take it away, CW3.
Hi, I'm Marianne, and I'm with my teammates Maggie, Elena, Amanda, and Ethan, and we will be presenting Wildfire Rescue from the Serious Games and the AI course.
So the question that we tested is about the ethics of self-driving cars, and it is, in comparison to humans, how does a pathfinding algorithm prioritize search and rescue in spreading fire? So our hypothesis was that overall, a basic pathfinding algorithm would be more self-destructive than a human player, since rescuing pedestrians, regardless of their location, is always prioritized by the algorithm, making the algorithm more likely to ignore self-preservation and the ability to rescue more pedestrians in order to deliver the ones that it can.
So this is our basic game state. There are 6 different important items: the ambulance, injured people, which is represented by a black eye, the hospitals, which look like hospitals, 3 different terrain types, which are essentially out of bounds terrains, impassable terrains, and passable terrains, a fire, which starts in the corner of the map, and batteries, which replenish your energy. How the game works essentially is the fire will spread over time. That's why it's concentrated in the corner of the map, and it will jump to random tiles close to where the fire is, and this will cause pedestrians to die. Our whole goal here was to see what kind of decision making would be best in this kind of changing game state, and how players and our pathfinding algorithm would prioritize which people to save.
Okay, so we have for you now a demo of a human playing our game. So we just wanted to show you what basic gameplay would look like. So we see here basic turning and moving forward, picking up batteries, which replenishes the energy bar that decreases with every step. And then picking up a pedestrian, which is marked by the eyes, and dropping them off at a hospital. You can see also that when a pedestrian is in the fire for 5 steps, it will burn and disappear from the map. However, you can still pick up the pedestrian that's in the spreading fire and move them around in the fire without them taking damage. Now, you can also see that the spreading fire is northbound, so it actually is more likely to travel in the north direction, but will also travel in the other directions. So depending on which corner this fire starts in, this can affect gameplay. And then this is our end menu. You can see the scores. And that's pretty much it.
So we have several end conditions, although they all entirely rely on the ambulance's energy value hitting 0. You have 3 choices of moves. You can turn right, turn left, and move forwards, and each move takes up 1 energy. Spending a turn in fire will cause an energy cost, and when your energy hits 0, the game ends. We made the fire cost a lot more than the move cost, so that there would be a significant impact for when the ambulance does spend a turn in fire, so that the player has to be more strategic with how they move. And our scoring system is based on how many injured people you can save. Picking someone up and taking them to the hospital gives you 9 points, and running over an injured person gives you -1 points. The goal of both the pathfinding algorithm and the player is to maximize the number of points obtained.
For the machine play, we used a pathfinding algorithm to find each move that the ambulance should make. The algorithm uses Dijkstra's algorithm, and the length of the path is defined by energy. Some energy values that we used were defined by gameplay. For example, if the ambulance steps forward or turns left or right, the energy will decrease by 1. If it spends a turn in fire, the energy will decrease by 3. If the ambulance collects a battery, energy should increase by 20, but we won't use this in our calculation because it will cause negative edge weights. Other than the energy defined by gameplay, we also added some other energy values to bias the algorithm towards certain behaviors. For example, if the ambulance runs over a person, we will decrease the energy by 20. And if it doesn't pick up a person in the current turn, we will decrease the energy by 5. Since there are negative edge weights, the algorithm must choose one of 2 choices for the path that it's going to take. First, It will calculate the distance from the ambulance to an injured person to the hospital and then to a battery, which is the path shown in red. If the ambulance has enough energy to make this move, then it will go in this direction. Otherwise, it will go directly to the nearest battery, which is shown in yellow. This is an example of the machine's automatic play. The game mechanics are exactly the same as human play with going forward or turning left and right. And the only difference is that the algorithm chooses the steps that the ambulance takes for each move. So the game doesn't require any input from a human to play.
So we collected data from 652 machine plays and 25 human plays. On average, the machines saved slightly more people, and this resulted in their higher average score. And the machines also had more turns per game, meaning that they lasted longer than the humans. However, this could also be because the machine will sometimes choose to fetch batteries that are closer rather than going to a person who might be farther away. On the left, we have a chart showing the object counts. So we have categories like the number of pedestrians squished, delivered, burned, picked up. And we also have a category for the number of batteries picked up. So out of 652 machine runs, the machine only squished one person total. This was due to the high penalty for squishing someone. And in comparison, the machines are slightly more willing to squish people in order to get to a hospital or battery, for example. One pattern that appeared during machine play was that when one injured is left on the opposite side of the board, the machine sometimes doesn't go pick them up and deliver them, and instead chooses to pick up batteries because there's this penalty for not picking up people. So it thinks that it's out of energy. And on the right, we have a graph showing the number of steps ended in fire. And while it might seem that the machine is more willing to risk going into fire to save someone compared to humans, one reason why the number of steps in fire is so high is that it will continue fetching batteries in fire rather than avoiding it and fetching a person.
After we conducted all of these tests, we found that to answer the hypothesis, the machine prioritizes the injured people that are closest to it and then the batteries. Despite the fire penalty, it is still willing occasionally to go into fire. So one of our top questions was, even if the pathfinding algorithm saved a higher percentage of people more often than human plays, is it more ethical? So that depends on what you count as more ethical. An example would be fewer people squished. And then this ties into our second question, when does success become a greater factor than ethicality? And again, this depends on how you define success. So for example, you could define success as the number of people delivered to hospitals, number of people rescued in fire, or number of times the ambulance escaped fire. And you can measure this by valuing either self-preservation more or altruism more. And this could go multiple different ways. And then our next question was, how would public opinions due to ethics impact implementation of a self-driving ambulance in real life? So this depends on people's current perception of AI and if they think that the self-driving ambulance will improve search and rescue over current ambulances. And what are the human flaws that we want to minimize in the autonomous vehicle so that it can best achieve its aim? So in game, we could perhaps measure the level of anxiety when players play the game, and also the psychological impact of UI in the game. So by conducting this experiment and comparing data between a pathfinding algorithm and human performance, we can identify patterns or tendencies in human behavior that an algorithm may or may not exhibit.
In a real-world application, which would ultimately be the goal of our project, we would likely require a more sophisticated form of AI than pathfinding. Though we definitely found success with pathfinding, especially given our time frame and project scope, there's definitely fallbacks. Firstly, it's an algorithm, which is a form of AI, but doesn't dynamically learn and change. And we could also think of this from an ethics standpoint, putting a literal cost value on the actions it does, including on saving people to calculate the ideal path. With reinforcement learning, however, it learns and adapts to its situations, which would be ideal for dynamic situations such as a spreading fire. though we feel that we have made steps towards improving the UI design, overall it's still less intuitive than we would like. By improving clarity and user experience, we hopefully would avoid skewed data in human play because of lack of understanding of the game itself, rather than because someone made the choice to play that way. Speaking of data, we found in particular we lacked having significant data to analyze. Firstly, we focused on only one kind of map, when running trials, as in the number distribution of batteries in hospitals, for example. So we'd be interested in how our data would be different on a different grid layout, say with only 2 hospitals on the map. Ultimately, with more time, we would definitely run more trials, both human and machine, to improve the accuracy of our current conclusion or maybe reveal some new findings. Thank you all for listening to our presentation. We sincerely hope that you enjoyed learning about our work and our findings as much as we did.
Thank you. And for our final team, Team DC2.
Hi, so we are Team DC2, and for our research project, we investigated how a stressed environment affects the paths players take during a game. My name is Ray.
My name is Rashida.
My name's Gabe.
I'm Rahel.
I'm Jeffrey.
So for our project, we wanted to investigate how players would react to a stressed game environment where zombies could move around and potentially turn pedestrians into zombies. We wanted to know if players would opt for short-term or long-term gameplay, or if they would take riskier paths like going into penalty zones such as fire or mud more often based on the setting they were playing in. As a group, we predicted that players would tend to take less risky paths in a stressed environment. We also thought that in a more stressed environment, the ability of the players to plan ahead would be hindered, resulting in a shorter average gameplay for those playing in real time. In this game, the player acts as an ambulance driver during a zombie apocalypse in order to try and replicate a simulation of what self-driving cars would do in the same situation. Players are rewarded for saving the injured and for squishing the zombies, but they are penalized for squishing pedestrians. Players are also penalized for entering zones like fire or mud.
And we made some game modifications as well. The 2 main modification game modes that we made is one where the zombie moves every couple of seconds, which would induce more stress. And then another one where the zombie moves alongside the player. So that would be like you make a move and then the zombie would as well. This would be like our control and be less stressed. We found other ways to stress the environment, such as allowing the zombies to like injure and kill the pedestrians. And then we improved the UI. And by doing that, we made a start and end screen, and then we had a legend. So that's our start screen. On the left is the turn-based movement. On the right is the real-time. The turn-based is, I'm moving pretty quickly, but it is moving every 3 turns I make, the zombies move once. But on the other hand, with the real-time movement, the zombies move approximately every 3 seconds. The zombies also have the ability to injure the pedestrians, and that can be represented on the legend with the 100% pedestrian, 75%, and so on. They're represented by several different colors. As you can see on both maps, there's some green, some yellow and orange as well, and some red too. And eventually the pedestrians will take enough damage that they will convert into being zombies. That's our end screen, and it lists some of the data points we selected.
So after we finished implementing our modification, we got people to test our data to test our modification and give us data in both of the 2 modes. We'd have the data displayed on the ending screen. And we analyzed it through Python libraries like pandas and matplotlib to effectively make data frames and graphs you'll see on the next 2 slides.
So looking at a side-by-side comparison, we noticed a few major points is that the total people saved by turn-based is more than it is for real-time, and the total people killed was less by a huge margin than for real-time. We also noticed that the score was about 10 points higher, and that the amount of turns taken was higher. And we'll go into deeper analysis of these in the next few slides.
Yeah, so located here is the score distribution for the real-time gameplays versus turn-based gameplays. And as evident, the turn-based gameplays had a higher score on average, with one outlier, whereas the real-time gameplays had a more varied distribution. While the turn-based graph has most of its points at a score of 18 or above, the real-time graph has a more even balance of low and high scores, with lower scores on average. This proves the efficacy of our stress factor. Players did worse in our real-time version, as time was a key stress factor that we implemented, whereas in turn-based versions, players had more time to think about the consequences of their decisions and make better choices. So featured here are box plots that portray the score distribution in a more statistically adept way. As seen here, the median for the turn-based scores were much higher, even over 10 points higher, along with the 25th and 75th percentile being higher. The range is much higher though, and the turn-based gameplays actually resulted in negative scores, while the real-time scores only resulted in non-negative integers.
So the interesting finding we had was revolved around battery usage. Every game, players would have 50 turns to squish as many zombies as they could and save as many injured as they could. However, if they picked up the item called the battery, the amount of turns they would have to do this would increase by 20 points. A trend that we noticed was that the amount of batteries collected and the score would be directly proportional, meaning that if a player collected more batteries, they would usually end up with a higher score. Another thing that we noticed was that in real time, the averaged amount of turns was 63, and in turn-based, the amount of average turns was 91. And looking at these two data points together, we realized that the cause of the difference of average points between the two is actually the amount of batteries they collected, meaning that the reason why real-time and turn-based have such a huge gap in points was because turn-based players tended to collect more batteries. And what does this prove? It proves that we were successful. The data we collected reveals that players tend to opt for short-term gains in real-time zombie movement, so the players tend to kill zombies and save victims instead of picking up batteries to elongate their gameplay. This resulted in a lower average scores for players in real-time environment. And this proved that in a high-stress environment, players tended to have their long-term decision-making and long-term planning hindered by the stress.
In the future, there's a few things we'd like to experiment with. We wanted to look at other factors like gender, age, or race to make players decide who they wanted to save more and see if their decisions changed based on the stress they were facing. We also might want to look at other stress factors like a timer or a distraction to compare with things like the real-time movement we were using. And we wanted to use custom maps to give us clearer data that wouldn't be skewed by randomness as much.
Thank you.
Excellent. Thank you so much to all our teams. It was definitely our pleasure. We were all very impressed. Thank you all to the audience for engaging and for the questions.